some more complexities that we face in optimization problems is I mentioned about the hierarchy. And one of the hierarchical problem I'm showing you here is a control system problem, where let's think of broom balancing, which is a very common, as if you take a course in control systems, they are going to teach you a problem like this, which are sometimes known as an inverse problem or broom balancing. It has different names, has come from different fields. But the problem is you must have done it in your childhood as well. Take a stick and put into your hand and try to make it straight up, right? You have done that. So there is a platform you have which you can oscillate and make sure that the stick is staying vertically up. It doesn't fall. So basically there are two things here. The control is applied on the base of how you're going to move it around. But how you're going to move it around depends on what's happening with the stick, right? Is it falling in front of you? Then you have to do something to make it not fall. If it's falling on one side, you have to do something to make it. So you need to learn that process of how to control it. So it's a typical control system problem. Actually, it's a hierarchical problem. If you try to say, okay, I'm going to do it optimally, what does it mean? Now, one thing is control. So eventually, I'm going to control it. It's not going to fall. But the other thing, when I say optimal control, then you're saying, I not only want to make it stable, I also want to make it as soon as possible, quickly. So this is a time optimal control problem, as they call it. So with time, we want to do it as with minimum time as possible. So when you have that, then there is a upper level problem, which is how am I going to move my platform? So there could be some variables. Let's say I'm going to use XY movement. I'm going to give a push in X direction and push in Y direction. So these are my two variables. At every time step, I need to decide that how I'm going to change my X and Y velocities with respect to time. And that depends on so many things in this dynamical problem that we have, right? So once you fix that, now you have to go to the lower level, which is the broom itself or the stick. And then you have a dynamics, because at the bottom of this stick, you have some force that's being applied. And then it has its own mass, and it's trying to fall in some direction and all that. So what happens then is that, so I need to look there. Is that right? Is that what you're saying? Oh, full screen. Yeah, that's right. Okay, so let me see if I got that. Control F1, Control F2. Oops, not that one. Where is that coming from? I need to be this one and Control F1. Okay, so here you have the lower edge of it, which whatever you are doing here get transmitted to this, and whether this problem will be stable or not with your X and Y velocity, let's say U and V, you require another optimization problem. So that one is, when you are solving that one, you have these velocities or the forces that you are applying here becomes your, they are not your variable anymore, they are coming fixed. So there is an upper level variables which are U and V. To the lower level, when you are solving this problem here, whether it will be stable or not, those U and V's becomes constant, and you solve this dynamical system. So solving the dynamical system or solving any equation can be considered as an optimization problem, because all you're trying to do, there is a left hand side and there's a right hand side, and you have to make the error between the left hand side and right hand side 0, right? So you construct an error function and then minimize. Now, of course, in this dynamical system, you'll have a partial differential equations, right? That will determine whether it is stable or not. So solution of that partial differential equations becomes the lower level optimization problem. So we'll talk about little more this way, and when we get to the bi-level problem. So there is one optimization inside the other optimization, and these kinds of problems are pretty common in practice, that there are hierarchies. Currently, we are working with a company called Dow Chemicals, where we have 3 levels of operations that we have. Those of you who are working in operations management would know that there are strategic, tactical, and operational level decision making you have to do. Strategic means you do once every year or once every 2 years. What kind of decision making? This would be very global, whether a plant should be here, whether a plant should be shut down, or increase its capacity. These major decisions you have to take. And then once you have taken that, let's say it's a supply chain management problem you're doing. So which truck companies would deliver your trucks or take goods from the plant and deliver it to the destination? That will be maybe done in quarterly manner or every 6 months. So that's a tactical level decision making. And then operation is daily. Daily what's going to happen, which truck is going to take what good and deliver where. So you see, if you go down from year to quarter all the way to daily, the level that you have is completely different, right? At the daily level you have very detailed, and at the yearly level it's very fuzzy, but you are making big decisions. So in a company, this kind of hierarchy always exists. You cannot treat the whole thing as one optimization problem, then you're not treating it properly. So there are algorithms that exist to take care of such things. So we'll talk about at least a bi-level optimization later. Now I mentioned computationally expensive evaluations, where you have an object and it is supposed to, for example, have some lift and obviously going to have some drag. So when you do a computational fluid dynamics simulation, you can figure out what is the flow pattern, how much lift there is and drag there is. But getting these things, you need to go to a computational domain and find all these, and these are time consuming. So if one evaluation, so let's say this is my design, this is the shape that I'm trying to come up with, an optimal shape, and I have some control points that tells how the shape is going to be. So for one shape to say how good is that, what is the objective function and constraint, I probably need to wait a couple of hours, because that's the amount of time my computer takes to do the whole flow simulation. So if one solution takes a couple of hours, if you need at least 100 solutions to come up with a solution close to even whatever is the optima of this, you cannot guarantee optima in such cases. So 200 times 2 hours, you can see how many hours is that and how many days that's going to be. You have to wait. So people are still doing it, but may not be spending that much time. They're doing all kinds of tricks, like parallel computing is one big applications in this. So your CFD solver should be parallelizable. Your optimization algorithm should be parallelizable. So that there is a hardware solution to this problem. Also, you need to think of software solutions, which should be very efficient algorithms. So can we make your fluid flow solvers very fast? So think of how algorithmically you can make them faster. Can you make your optimization algorithms fast so that it doesn't require too many evaluations? May not be even 100. Maybe you can do it with 50 or 60 of them, then you can reduce it by half. So we've been doing this for many years now, while I was in Kanpur and back there. So we've got specialized computers to handle and mostly distributed computing. Just to give you an idea, we are solving one problem about 6 months ago, which would take about 18 hours to solve. It's a irrigation problem. We are simulating how water permeates through soil, and the whole process uses FEM solver, and it takes about 18 hours to get one optimization run. We just bought a distributed computer with 52 nodes, and we have reduced the computation down to about 40 minutes now. So previously, my PhD student would give it a run, and next 18 hours he is free. Okay, so he was getting bored what to do, because unless some results come, he doesn't know how to set up the next one. Now that we have this computer and some software solution to the problem, in every 40-45 minutes he has a solution. Okay, so he can plan a lot of simulations in a day. So anybody is working on optimization area and trying to solve practical problems will need hardware and software solutions. That's the only way to go. But these are possible. Although initially, when you look at it, it may be intimidating that one solution takes 2 hours. How can I even do optimization? And this is an excuse, more of an excuse in today's world, with so much computing power and so much technologies in and around. It's foolish for you to just give up. There are so many ways you can do these things. And another interesting thing is, whatever you do here with the, let's say, hardware solution and software solutions, chances are that not many people have done anything in that direction. If you particularly reduce 18 hours to 40 minutes, it's always publishable. So that's another thing, being in an academic environment, that you are looking for publications. And it's a news to the community. One aspect is that you could address such a problem. The other thing is that you are considering practicalities, practical aspects. So the fact that we've gone down from 18 hours to 40 minutes, we are not solving the same problem, because initially we had everything static. But now that we could do in 40 minutes, we are saying, okay, let's consider uncertainties in the precipitation, the rainfall. So it's a farm problem we are trying to come up with to a farmer, trying to say how much water they should put every day for the irrigation. And then that depends on what is the soil quality. Is there already water in the soil or not? And then how much rainfall does this place get? So initially we assumed everything fixed, and one run took about 18 hours. But now that you could do quickly, we can say, okay, we can look into the internet and find out what is the average rainfall. Even for last 10 years data we can get at a particular place. Okay, how in a particular day of the year the rainfall had been. We will get a distribution of the pattern. And then we can take that as an uncertainty, right? So next year if we do that, we don't know how much water is going to be. But if we have 10 years of data, we can actually make a prediction of how it's going to be like. What will be the average and how much is the standard deviation. So we could actually go and become more and more practical if you can reduce some of these time, computational time. But these are practical complexities that we often face. Okay, so what happened here? I can move to the next slide. Yeah. Okay, I mentioned to you about the multidisciplinary. This is a slide that I got from Professor Bob Fulton from Georgia Tech. It's really nice. If you want to design an aircraft wing, let's say, or the whole aircraft from different disciplines point of view, here you can see on the top if a production engineer would design an aircraft. Okay, this would be very simple with rectangular kind of beams and then just make the plane out of that. If you say weight is your only concern, you are going to have a very flimsy looking plane which will probably have the least weight and not be able to carry too much weight. If you want to do aerodynamics way, then everything will look very sleek from an aerodynamic point of view. Similarly, armament, loft, you want to carry a lot of baggages. Then stress, your stress, really concerned about the stress. Then everything should be an I-beam, because that takes care of the stress very well, right? There are other things, electrical, and so this is a sketch that he has drawn to say that the same object, if you think from different groups, different fields, you will have a different solution. But obviously the aircrafts that we see around us is not any of them. It's a combination of all of them. So that's how you get into this multidisciplinary concept. And when you're optimizing, you have to consider every discipline and how they should be put together. So unidisciplinary design is what is followed, but practice is full of multiple scenarios. So this is multiple, not scenario, this is multiple discipline. There is a multiple scenario which I mentioned to you, that once you have designed something, this will be probably used in many different ways, or before you even implement, like that big transmission tower example I gave, right? It has to be considered from different loading conditions before you even install it, or during its installation and during its operation, it may go through several different loading conditions. So those are called multi-scenario optimization. Okay, so these are about different practicalities through a number of different problems from practice where optimization can be used. Now let's say a little bit about algorithmic issues and algorithmic difficulties. Most optimization algorithms are dependent on what solution you're starting with, unfortunately, because when you go to linear problem solving, that's not a problem. When you go to nonlinear problems, it's very, very sensitive often to the initial solutions. Now we try to come up with algorithms that are not that sensitive. So you can start with any initial point and it should arrive at the same solution. But most of the point-based methods, unfortunately, are very sensitive to the initial points. So you need to do some parameter tuning. Okay, so initial solution is one thing. Other thing is every algorithm will have a parameter. I will show you some algorithms. You will see that every algorithm has at least one or two parameters, and the performance of the algorithm depends on what parameter values you're using. So which means you're solving a problem and you got an algorithm, say learned from me or got from the internet or some paper. You will see there are some parameters in it, And now you have to tune it for a while to your problem to see where it works well. So there is a learning curve before you actually become successful with the application. I will talk about the no free lunch theorem, which actually says that no algorithm is better than another if you are interested in solving all problems. So that has several implications which I will mention. But there is another issue with most of the optimization algorithms is what is known as a curse of dimensionality, which means the algorithm I described to you will work pretty well if you have very few dimensions, like 2 dimensions, 3 dimensions, maybe 5 dimensions, 5 variables. But if you go to 50, 100, 200, the same algorithm doesn't work that well. So that's the issue. Most of these algorithms were designed or developed thinking of low dimensions and testing on low dimensions, but they often do not work. So anything we come up with, a new algorithm we come up with, we make sure that we do a scalability study, at least going up to about 100 to 500 design variables as well. Okay, so that's a very important thing. Many algorithms, including most point-based methods, have a local perspective, which means if you start from a point, initial point, it will go and find and give you the nearest local optima. That may not be the global optima. So many algorithms have the local perspective simply because whoever has developed that algorithm was thinking of local information. So all the algorithm can do is get stuck into a local optima. So if you have to use these methods, you have to try many times with quite different initial points so that sometimes you hit on the global optima. So it's a sort of like a chance. So these are some issues with some of the methods, and when we get to the population-based algorithms, all you're trying to do is alleviate some of these problems, eliminate some of these problems. So I'll talk to you about this when I get to genetic algorithms, how we can overcome some of these issues with point-based methods. But one thing is true across all algorithms. Any algorithm that we have for solving any arbitrary problem, which could be a nonlinear problem, there is no algorithm with a convergence proof. So if you're asking me, sir, can I have one algorithm with a proof that any problem I give it to him, it's going to give me the optima guaranteed? The answer is a big no. Okay, because somebody asked me yesterday, right? And the answer is no. Nobody has found that algorithm yet. And no free lunch theorem actually says you can never find. So don't try, okay? Because there is a proof that says it is not possible. So when you have such a scenario in a field where you can never have an algorithm that will have a guaranteed proof for solving any arbitrary problem, many of the people just go away from the field. It says, oh, then what's the point? But practice is not practice doesn't require proof all the time. I mean, I've flown here, many thousand miles. I mean, you guys go also travel, right? Take a flight going somewhere. Is there a proof that the aeroplane can fly? There is no proof. There is no mathematical proof. Okay, engineers, basically the Wright brothers long time ago, on the wind tunnel has shown that if you have that wing shape, the shape of the wing, which is like aerofoil, it gives you maximum lift and also minimum drag. So they found one shape that has both the properties that they're looking for. Well, when they talk about maximum and minimum drag, they're not mathematically proven. They are, again, maximum, minimum with respect to other shapes that they have investigated. There is still no proof that that is the shape that's going to fly you forever or can fly you. But it is tested well, and so many years the airplanes have been on the sky that we don't even think about it, that there is a proof, right? I talked to you about steel being made in blast furnaces, right? Again, there is no proof that the steel you get will have uniform strength all over. But we are making bridges and we are, going over them and everything. We live in such houses made out of steel. So engineering is very different or has a lot of practicalities from science. So that's how science and engineering kind of differs a little bit. Engineering has full of scientific facts in them, but we are not interested in whether there is a guaranteed proof or not. We do a lot of testing to figure out, in most cases this is fine, we can live with it, and then we go ahead and do that. Similar kind of principles you got to have in optimization. If you go and talk to what people do in mathematical optimization group. There are places, I think in IIT Kharagpur also, there are some people working in mathematical optimization. IIT Kanpur, there is a big group. They are only interested in algorithms that has proof of convergence. So if you look at their scope of work, they are only restricted to convex programming, linear, quadratic, that kind of programming. But any of these problems I gave you, if you formulate, that will be far from these problems. They will not be linear, they will not be quadratic, they will have all kinds of complexities in them. So when that happens, they will simply give up their hand and say, sorry, I cannot solve it. But as an engineer, we cannot say that we cannot solve it. We'll have to find a solution, right? So engineering optimization, sometimes I say these things as engineering optimization or applied optimization because I am not going to give you proof, okay? But I'm going to show you examples, runs over many times that we do, that every time it gives us a solution that we can live with, that is much better than what we have before. So there is a science that tells us that this is what's going to happen if you follow this method, but then it may not tell you. There are several reasons why it may not take you to the optima. One is that the Carson dimensionality comes in. I will show you one example where you can be arbitrarily close to the optima. Okay, so if the optima is here, you can get arbitrarily close to it with a very fast computational time. But if you expect it to reach the optima, it takes exponential time. So something that will take maybe few hours to get there, if you want to go from there to the optima, which is just the iota change in the function value, it might take few years, from few hours to few years to get there. So the question is it practical for us to really wait just to get so much advantage, little bit of advantage on the solution? And oftentimes the answer is a clear no. So we just try to then look for approximate algorithms for optimization. And for all those purposes, NFL theorem and the fact that we don't have convergence proof doesn't bother us at all. Okay? Industries are looking for, they give you a problem, they're looking for, here is my current solution and here is the problem I'm having. For example, the Tata Steel example I gave you for the furnace, they were burning a lot of fuel to reheat these blooms. So they're wasting a lot of money. And in fact, they're putting so much heat inside, all the refractories were going down in every 15 days. So 2 weeks they run, another week they shut down because they have to change all the bricks inside, and then another 2 weeks again. So imagine how much waste of money they were having. Then they're forced to consult someone who can help them in redesigning the whole thing. So their goal is, can you do it better than what we are having now? Can you just make it in a way that we don't have to replace the bricks in every 1 year, less than a year? If you can do that, you have actually saved a lot of their time and efforts and money, right? They're not looking for the optimal design, which could be 5-year long refractories will survive. But they may not be looking for that. If you say, okay, right now they're doing every 2 weeks, if you could do 1 year, they're more than happy. So oftentimes our target is that, okay? So when you do that, then you are not finding the optimum, but you are finding better than what they have. So in those purposes, these are absolutely fine. And also the fact that optimization literature is such that you cannot find one algorithm. You can never find one algorithm for all problems. Okay, so now there are some issues with practical optimization. When you're thinking of applied optimization or optimization for practice, I mentioned to you this already, but let me highlight a few of the other things that people in industry thinks when you do single objective, your solution is too specialized. Okay, so oftentimes that happens. In fact, in the same furnace design problem, reheat furnace design problem, there were 3 people who were helping me there, showing me around. So I went and saw the furnace and came back to the office and now trying to formulate what are the constraints. Constraints, no problem. Everybody gave some things that what is allowed, what is not. When it came to objective function, I asked them that what will satisfy them, what we try to achieve in terms of performance. That's where I found each of them had a different criteria in mind. One of them said I have to increase the refractory life. The other person immediately stopped him and said, no, that's not a big issue. The cost we have to reduce. Okay, of course, refractory life has some effect to do in the cost, but he was more interested in cost. Okay, the other person says, no, much of the time we have these blooms, they get stuck onto the conveyor belt and it doesn't fall. It gets stuck because there is slack formation and these are reheated, so they kind of get bonded. So can we make it in a way so that there is minimum slack formation? So everybody had a different view on the same problem, and I realized then the first time that in practice, objective function is where people have difficulty converging to one idea, because these problems are not single criteria problems. You have to satisfy a number of different criteria. So when you have that, and when you have multiple people doing it, there is not much agreement. So each of these problems needs to be looked into from a multi-criteria point of view, so which we will talk about later, right? Variables and parameters sometimes are uncontrollable, that they say, okay, you told me that I could set up this burner at this temperature level, okay, but I'm not able to, okay, because there are several reasons. The fuel that you are getting is diluted, is not what you assumed it to be. So you are sending so much flow rate of the fuel, but it doesn't have that much effect. So not everything is in your hand, right? So the sources are different, so there are uncertainties. So you need to consider these uncertainties in optimization. Okay. I mentioned to you about solutions being trivial, like 0, 0, right? That kind of stuff. So you need to make your optimization problem more realistic. You have to bring in more term into it, or another constraints into it. So you need to do some of this. So it's an iterative process. Sometimes, again, another story, when I was visiting Tata Motors in Pune, so I was there 2 weeks, and I was then just joined IIT Kanpur. So I was interested in knowing the industries in India, what kind of problems where optimization can be used, so that I make them aware. So I knew some people there, so he arranged a 2 weeks visit for me, and every day I'm visiting a different plant, okay, over there. And a nice thing about Tata Motors is that it's compartmentalized. Every functionality of the car has a different department, like an axle department, a wheel department, and a cab department, an engine, and all suspension, different departments. So I thought every of these departments may need to optimize on their own scope, whatever they can change. So I was going and visiting, telling them about optimization, and to my surprise, not many people knew about methodologies of optimization. They said, yeah, we optimize, but then when I go and ask them, it turned out that 2-3 solutions they compare. Most cases they compare with another solution, and then that's it. They said they have optimized. So after the first week, then wherever I was visiting, there was a rumor around, and there is someone who has come from IIT Kanpur. He's trying to change the whole company. So don't listen to him. Okay. So second week I was not accepted well. Okay. And I then started asking around and found that the changes that I was talking about, they thought that it's going to change their life. The whole plant has to be shut down and everything. I mean, when somebody asked me that, you're not talking about that, right? I said, well, if you can, I can talk about that. But because as soon as I enter the company, even now I think it is a similar situation, but I have not gone there for a while, but I don't think things will change. I don't know if any of you have visited any automaking companies in Jamshedpur or Pune or any of the other places. I haven't seen that abroad. I've been to Volvo and Ford Motor Company and GM. I haven't seen that. So only here. But again, I don't know the latest situation. As you enter the company, so this was the truck in Jamshedpur. I'm talking about the trucks they make, right? All these trucks are lined up on the roadside, and they're new, right? They're also lined up. So I asked the person who was my host and said, "What are these trucks doing here?" They said, "Oh, something is missing in every of them. I mean, they just have the wheel, the engine, some basic that is needed for it to roll out. And then something is missing, some control system, some this, some that, and because the parts haven't come yet. There is a tag in every one of them, what is missing. So when the parts come, somebody will physically come to this location and fix it, and then it will go out of the company." So they do that, they roll out because they show the statistics, how many trucks they have produced every day. So if they're stuck in their plant itself, within the plant, then they cannot record that number, right? But it's a complete mismanagement in the sense of the supply chain management issue. Okay, so I asked them that today's world you could do much better job with the supply chain, because they are relying on the suppliers and they are not supplying in time, but they have to really roll some of them So these are uncertainties, right? So this company is relying on suppliers to supply these things, and there is uncertainty there. Uncertainty is also there because their head office in Mumbai says, okay, next month you have to produce this particular truck by so much amount more, and that one don't do so much because we don't have that much order. So they also produce trucks based on order. So suddenly the order can go up and down, and that's not their control. It's controlled by who is going to buy it, right? So now suddenly they have to produce, let's say, double the size of this truck. They don't have that much parts. Okay, so they have to wait. So they said, how can we solve that problem? Okay, I said, you may reduce the problem. You'll not be able to solve it. You look at, because you're not producing trucks just today. You've been doing it for many, many years, and these suppliers are with you for a long time. There is a study you need to do, how they have been doing for the last 5 years, 10 years, how the market has been for different cars. You need to study those things. So these are outside their scope. They are designing truck. Why would they study all this? But it's not an isolated thing, right? It's the whole environment, it's the surroundings, who is buying your car. You need to understand their philosophies. So optimization is not just what you are interested in producing, but how is that going to affect? Because otherwise, you will have such a scenario. And now that I'm abroad and seeing companies, and I ask myself, how can they do it? And then you go and ask them, they say they do these kind of studies. Otherwise, they will not take the order if they cannot do it. Okay, so that they don't have these kind of situations. So there are solutions to these problems, but you need to first understand where the sources of these problems are, and then studies can be made. And so if you do a 10-year study, you have a distribution of every month during the year how these changes come about, so you can be ready, right, with that kind of statistics, so that you minimize such mismanagement. Anyway, so it may think like revolutionary to some people, but if they are willing to change the whole setup, including who is buying it, the order and everything, we can do it. But that will be a much bigger optimization. It may require enhancing some part of the company or reducing some part of the company. If they're willing, it's possible to do. But you don't have to be such revolutionary. You can go down to your own department level. So if you are doing only, for example, axle department, so you're only interested in the axle, how much diameter it should be, axle to axle distance for stability and all that, and you have maybe 10 different parameters that you can change. So your design variables can be only those, and rest of the thing, like the engine capacity and cab, how will it look like, you just keep it fixed because they're coming from other departments. So you can be within your own scope and optimize the system with your own variables. But if you have the liberty to change a much bigger scope, you can do that as well. The other questions that practice can come in is for someone who is not working in optimization and want to use one method. Once they go and look into the literature or any book, they would see there are lots of methods. So which one to use? It's a common question that I get. For that, you need to take a course like this to understand which algorithms are good for what kind of problems. Unfortunately, there is no algorithm good for all problems, right? And they have not taken that. So there is a learning curve again. One can learn, doesn't have to take a course. One can learn, but some reading and some exposure with an optimization expert would be a good thing. Now let's get to the no free lunch theorem before we conclude this lecture note. So it was proposed in 1997, only recently, right? It's not too long considering optimization is practiced since World War or even before. What it actually says is this: if you have two algorithms, A1 and A2, A1 can be something you have designed in your PhD thesis with a lot of sophistication. You thought, you experimented, and you came up with this very nice method. A2 can be a very lousy method, like a random search method, for example. Okay, so one can be very good, one can be very bad. But you are interested in solving all possible problems. Any optimization problem anybody can come up with or that you may face in your life, you want to solve using your method A1 or A2. Now let's say I apply A1 to all problems of F1. Now when I'm applying, I'll get some result. So let's put a performance measure on that, saying how good A1 has done on problem F1, problem F2, and so on and so forth. And then I get a one number out of an average maybe of all those problems that A1 has applied. let's say the performance measure is P1. And when I do that, I note down how much time it took or how many evaluations it took to solve A1 to solve F1. I'm going to give the same resource to A2 also. When I'm applying A2 to the same problem, I will give the same amount of time and function evaluation, same resource, same computer to solve it. So there is no biasing for the resources that I'm giving for algorithm A1 to algorithm A2. Okay? A2, then I apply to all of them and I get an average measure. Let's call that P2. They have done a 3-page proof showing P1 is equal to P2. Okay, so that's the no freelance theorem. What does it mean? That means doesn't matter which two methods you are using, algorithms you are using, if you're interested in solving all problems, their average performance is identical. So if your algorithm is doing well on some problems, you should immediately know that there exist some problems where your algorithm will not do well, to keep the average down to the same level. All right. So this then says you can never have one algorithm which will be best for all problems. The culprit here is the word all. We are actually, so there's a bit of story here as well. So this one started, first time they proved it is around 91. Okay, these two gentlemen, Wolpert and McCarty, and they belong to our group, our field. So first we had an email group at that point. So they first wanted our opinion of what they think, because this sounds like very primitive and very negative in results, right? That then what's the point for me to come up with a new algorithm if that's the case, right? So they were a little doubtful, so they sent the whole paper with the proof to look at, and some of us have looked at and started corresponding with them. Initial reaction was, your proof seems to be correct, don't publish it because it's very negative. We need more justification and more investigation of why this is true before you publish the result. So their papers were not accepted. So finally it appeared in 97. So it took 6 years before the paper was in print. But then people realized it's the word all that they used in their proof which is making it. And nobody is interested in solving all problems. So when you are solving, for example, some of you are in chemical engineering. So you are interested in solving chemical processes maybe. Some of you is in composites. You're solving that. Some of you in mechanical engineering doing gearbox optimization, aerospace, all these different things. Every problem has a property, but every problem has a class of problem. This is a problem class. For example, a process optimization, as long as you stay within the same kind of production, probably the optimization problem that you have will have similar structure in their objective function and constraints. So they all belong to the same class, except that the numbers are slightly different from one to the other. But if you switch to a gearbox design or a traveling salesperson problem, a completely different problem, right? So what this no freelance theorem also says, sorry, I don't have it here, also says is that, so I wrote it here, it breaks down for a narrow class of problem. The NFL theorem breaks down for a class of problems. What that means is that if you're interested in solving a class of problem, you can find one algorithm that is better than others. It's just that when you then take the algorithm and move to another class, it may not do well. And the algorithm that did not do well in this class start doing well here. That's how the average gets to be the same. But if you say right up front that the algorithm I have come up with is good for these kinds of problems, and you give the structure of the problem that you have designed it for, you're absolutely fine. So people understood the whole thing, and then now they become more aware. So what happens is anybody coming to give a talk or a PhD student defending, and he makes big claims like my algorithm can solve all your problems, or I have tried and my problem, I've tried so many problems, every problem it can solve. You just cool him down little bits and point him saying, do you know no freelance theorem? I heard that so many times. Okay. As soon as you say no freelance theorem, and people get straight put into line and saying, oh, okay, not every problem, but these are the kinds of problems. So it's always at the back of your mind. It's good to know that you can never find one algorithm for solving all problems. So before you design your algorithm, make sure that you specify what class of problem you're trying to solve. That's why a big example is linear programming. Everything is linear. So it's one class of problem. You can come up with one best algorithm for that class. But if you take that algorithm, try to solve quadratic programming or try to solve nonlinear programming, it may not be working very well. Okay, but you said upfront this is for linear programming. Okay, so that's the whole idea. Okay, there are a couple of thumb rules I want to say. First is use as few variables as possible. Don't unnecessarily increase your variable set. I mentioned to you constraints can be of two types, greater than equal to and inequality and equality. Within inequality, there can be greater than equal to and less than equal to, but we know how to move from one to the other, right? And equality constraints are hx equal to 0. If hx equal to 0 is a linear equation, we talked about yesterday that you can actually convert it to a, you can actually take advantage of that constraint. You can replace one of the variables with that. But if hx is a nonlinear functions of variables, then you are in big trouble. So there are ways to alleviate the problem I'm going to show you in the next slides. But let me skip this one. But this actually says the whole flow chart of how you actually do. And you see this, the first you got to have the need for optimization, then choose design variables, formulate constraints, objective function, which we talked about yesterday, set up variable bounds, then choose an algorithm based on all this formulation, and then apply the method, and you probably find some solutions that's not acceptable because something is missed. Then you go up and put some of those back and then come back up again. Here is the second thumb rule, that try to avoid complex equality constraints, as I just mentioned. So if you have an equality constraint like deflection, delta x is equal to 5, you want exactly some point to deflect by 5 millimeter, let's say. And delta x is a nonlinear functions of x. Okay, then you have difficulty satisfying the constraint. What you can do, you can relax the equality constraint by saying, okay, I'm going to say delta between 4 and 6. Or if that's too much, then you can say 4.8 to 5.2. That way you are providing a feasible window to the algorithm to work. When you say a nonlinear equality constraint, that means every point that falls on the constraint boundary is only feasible. That's too much for an algorithm to handle. You provide a window by relaxing it. What you usually do is we start with a bigger window. So let's say 4 to 6, and 5 was allowed, but we say 4 to 6. And as we go with iterations, we reduce this. After first iteration, I might do it, let's say 4.1 to 5.9, and then like that I can keep on reducing. Eventually I get down to 0, 5 plus minus 0 eventually. Okay. All right. Oh, this duality, this is also called the duality principle. So if you have a maximization problem, let's say maximize this function here, but all you have is an algorithm that minimizes, you can still use that code, use the minimization code to solve this problem. What you do is multiply this by -1. So when you multiply this by -1, your function becomes like this, but the optimal location doesn't change. And that's true also for constraint optimization. The optimal location will not change. So if you have a minimization code and you have to solve a maximization problem, you multiply the objective function by -1. Don't change the constraints, just the objective function, and solve it using your code. Whatever value you get, now we'll have a minus value of that. You just multiply that objective value by -1 and you will get back the actual objective value. Is that clear? Okay. All right, let me skip that now. And so basically in this lecture 1, we talked about different problems that comes from engineering which can be solved through optimization route. They are getting quite popular now. I can see that because I am kind of dealing with industries for various reasons. Some of these advanced practicalities that we are able to introduce in the optimization algorithm. Formulation of the optimization is important, and this is what we have been talking about in this first lecture. The formulation issues, the complexities the problem have, and little bit of algorithmic issues. As we go along with algorithms, we'll point out some more of those difficulties. So hopefully this course will prepare you to have a good understanding of optimization problems and the algorithms. Okay. So yeah.
Would the NFL stand true for like hybrid algorithm?
Any algorithm, any optimization algorithm. One of the ways to look at it is this. When you say all, you are actually saying minimization and maximization problems all. And you are not using duality principle for converting maximization. So if you have an algorithm that minimizes and you are solving a maximization problem, obviously it's not going to give you the maximum. So this is a very high level way of kind of justifying this algorithm, is that half the problem, when you develop a minimization problem algorithm, you can only solve half the optimization problems, considering the whole class. So it's not a surprising result to me, but it's good that we know it. We get reminded every now and then, just to be not able to make big claims. Okay, but it also forces us to focus on a problem. So there is a problem algorithm connection that you need to build up eventually if you want to be an expert in this area. Okay, so let's move to lecture 2 now. Let me see. Yeah. Question? Go ahead. Yeah, I'll come to that at the very last day. We'll give you details of that problem. Yeah. Now it will be a little premature because this involves 14 objectives. So we'll get to that later. Okay, yeah.
The person who is solving a dynamic problem in time domain, problem sometimes we face that the response sometimes becomes positive and next time will be negative. Suppose if on the displacement, it will be some moment it will be positive and second moment it will be negative.
Mm-hmm.
And even if you consider stress also, positive stress, negative. So how to which optimization technique would you put for such type of problem?
No, what is your objective function here? Yeah, so you need to write down the damage function out of all these things, right? And then you want to minimize the damage. So the damage function you have to minimize, and any fluctuation can be there in the variables or whatever you have there. But as soon as you write down the objective function, you are trying to minimize and maximize. So I don't want you to get confused with what you have been doing, and straight away, thinking it like a variable or an objective. Or first thing you need to have is, in my optimization problem, I mean, we spent so much time so far, right, where I try to make it very clear of the differences between the objective function, the constraints, and the variables. So I don't even know what you're talking about when you say they're fluctuating. Is it the variable? Is it, you said, a dynamic problem, which we have not talked about yet, the dynamic problem, how to handle dynamic problem. So it's very easy to get confused. But think about very simply to start with now. And some of these questions can be hold on till later on, because it's easily you can get, because you're dealing with functions, fluctuations, y versus x, and I'm showing you y versus x, you can easily get confused. But don't get confused. Just stay with me with the simple problems first. Once the understanding gets matured in your mind, then you can think higher. Okay. All right. So first, what you're going to do is single variable unconstrained optimization. Let's start with that. So in this lecture note, we are going to talk about now some theory. So there will be some math now. So far we haven't talked about too much math. It was just mostly descriptive. But to understand the properties of optimal solutions, we need to get to the math a little bit. And I'll try to make it as minimum as possible, whatever is needed. So first I'm considering a single variable problem. Okay. Just a single variable problem. So we have f as a function of x. It's a very simple function you can think of, like fx equal to x squared, for example. Very simple function. It's a single variable function. So what is the property of the optimal solution? This all of you have done in your high school or even in your undergrads. Is you take the derivative of f with respect to x. At the optima, derivative has to be 0. And if it's a minimum point, the second derivative has to be positive. Right? These are the things you know from your earlier days. All right. I want to now make it a little bit general. The general rule is given there. Identify the first non-zero derivative at the point x. So first what you have to do is solve df dx equal to 0. Take the derivative, solve it, and find what values of x is making df dx equal to 0. There could be 4 or 5 values of x that's making the derivative 0. Okay? So note down each of these. Now at each of these points you compute the second derivative. Okay? Let's say second derivative is also 0 at one of the points. Then you do third derivative. So that's also 0. So keep on doing that till you find the first non-zero derivative at that point. Let's say that order the derivative order is n. If, okay, so now here I have some mistakes in your slide. Change it. If n is even, I just changed it this morning. This should be not odd, even. If n is even, look at the sign of the derivative. For example, here, in this case, the first non-zero derivative happens to be 2, right? When I do the second derivative, first derivative is 0, second derivative is non-zero. So n equal to 2. Because it's even, now I look at the sign of that derivative. Is it positive or negative? If it's positive, it's a minima. If it's negative, it's a maxima. Okay? But if n is odd, let's say this is 0, d2f del x2 is 0, but d3f del x3 is non-zero. So that means n equal to 3. Third order derivative is non-zero. And then that order n in this case is 3 greater than 1, then it's a saddle point. Now there are, so when df dx is equal to 0, that can happen for 3 reasons. One is that that point is a minima, that point is a maxima, or that point is a saddle point. A saddle point is when you go in one direction, the function increases. When you go in the other direction, the function reduces. So it's like a saddle of a horse. Okay? Derivative is still 0 at that point, but if you go towards the negative side, maybe function value reduces. When you go on the positive side, function value increases. Okay? So if your first non-zero derivative is an odd number and is greater than 1, then it's not a minima, not a maxima. It's a saddle point, also known as a non-inferior point. Okay, so there are several names to this, are known as an inflection point as well. So these are different names, but bottom line is they are not minima or maxima. The only minima and maxima comes if the first non-zero derivative is an even number, and the sign will tell whether it's minima or maxima. So this can happen at d24, dx2, dx4. If that is the first non-zero derivative, so n equal to 4, now all you have to see is what is the sign of that derivative. Okay, that will determine minima maxima. Is that clear? So it's a bit generic rule which you probably didn't know. Because if df dx is equal to 0 is non-zero, let's say df dx is non-zero, then it cannot be even minima, maxima, or inflection point. So if n equal to 1 and it is non-zero, that means df dx is non-zero. You understand what I'm saying? Yeah, so what is n equal to 1? What does it mean? N equal to 1 means df dx is non-zero. So that's not allowed. First, this has to be true, and then only. So n has to be greater than 1. Okay. Now for maximization problem, of course, this one just, I mean, most cases you are done with the second derivative. But some cases you can be, second derivative becomes 0. That doesn't mean it's not minima or maxima. It can be minima or maxima. Then you have to just wait some more derivatives. Okay, but the problem is this, you need to compute the derivative if you want to use this principle and solve problems in practice. And derivative computation is very expensive, as I'll show you later, and some problems may not even have existence of derivatives. But for all our homework purposes, you will use this definition because you cannot use an algorithm in a short time. So you will use these mathematical conditions. Okay, before I go to the multivariable, there is a concept of line search that comes in multivariable search. A line search is, although you have a higher dimensional space, let's say a 2-dimensional problem. So I have x1 on this side and x2 on that side, so I have a 2-dimensional space. Everyone that you're sitting has a coordinate, has a x and y, right? Now let's say I'm going to start from point here and I want to go towards the door. So that's my line, and there is an objective function I have on top of us that says everywhere you're sitting, let's say your height. So if I ask all of you to stand up and make a surface of the height, and I'm looking for the person with the maximum height, for example. Okay, so somewhere there is a maximum, and unless I compute each one of you, if I compute each one of your height, then it will be an exhaustive search, and that will consume all of you to be computed, and then that's not a very efficient search. But if all of you are kind of seated in a certain manner, certain orderly manner, that the minimum height person in neighborhood persons also have smaller heights. So if I arrange you that way, then there is a structure in my function, right? And now I can use some local information to get to the maximum height person very quickly. Right? So that's the idea for the optimization. But in this particular case, I'm saying I'm going to draw a line from here to there, and I'm interested in only finding the minima along that line, not the optima of the problem, but the optima along the line. It's also a single variable search, right? Because what happens here, if this is my x and I'm going along this direction s, these are given to us, x and s, all I need to have a point on the line is one number, which is how much distance I have to move from this point to the line, to that point on the line. So there is only one variable a that I have in this problem, although it's a two-dimensional problem. I could actually extend this to 100-dimensional problem. And if I'm doing a line search in a 100-dimensional space, it's still a single variable search, right? Because the line is specified, all I need is one number that says how much I go from the starting point to any point on the line. So any point on the line can be written like this way. This x at a particular iteration t is known, s is also known, all I need is a. So the whole set of 100 variables is a function of a only, so single variable. So I can use this single variable definition that we talked about to find the optima along a line. So this process is called a line search or a directional search. Okay. So how to solve the line search point, to find the optima? So you see, given the function fx, my goal is to now find x star that is going to minimize it along this line. And as I said, this x can be now written as a function of a. Okay. So the optimality condition, now if I substitute this x into f, this f can be two-dimensional problem. So x can have, let's say, two components, x1 and x2. But as soon as I do this transformation, x1 is a function of a, x2 is a function of a, right? So my f is actually a function of a only. It's a single variable function. So I can use these two optimality conditions we just talked about. Differentiation of f with respect to a should be 0, and second derivative of a with respect to a should be positive. So if you do a chain rule for the derivatives, because f now is a function of x1, and x1 now is a function of a, and f is a function of x2, and x2 is a function of a, you can keep on doing for other variables if you have. Basically what you end up doing, this becomes the derivative of f evaluated at xt transpose the gradient of x with respect to a, which we can see from here. If you take a derivative of x with respect to a, you get st. So this product, this is a vector and this is a vector. This vector dot product should be equal to 0 at the point of a. So by solving this, you can find a star. I'll take an example and you'll see. So once you find the a star, then you check simply the second derivative and see if this is positive. That's it. Then you substitute a star here and you get the new point. So here is an example. So let's say I've got a quartic problem, two variable, it's a polynomial function of order 4. Now my problem is to minimize this, but I'm not going to find the minimum of this problem. I'm going to do a line search. So here is the x1, x2 contour plot of this function. Contour means if you go through this line, any 2 point on the line has the same objective function value. So this is how you show a 3-dimensional problem into 2 dimension, because you have x1 here, you have x2 there. How do you show the third dimension, like f value as a function of x1, x2, like the surface? I'm not showing you the surface here. What I've done, I have a surface on this place, I have cut it at different level, and I'm showing how the contours of that cut surfaces will look like. So as you see that this one has the highest value, and then it comes down, and the optimum is somewhere here. Okay. So for the line search, I'm starting from this point here, 0, 4, and I want to go along 1, 0, which means in the x-axis direction. So this is my direction for line search. This is my initial point. I want to find where is the best point. Now you see, with the contour, as I am going this way, my function value will reduce, and eventually when I start to cross from here on, the function value will start to increase again. So it decreases and increase again. So if I show the function value, it will drop like this and it will go up again. So here there is a minima along the line here. So how do you find that point? Using the procedure I just described. First you write the general expression for any a from here will be 0, 4, this point, plus a times the direction, a times the direction 1, 0. Okay. And so if I manipulate this 0 plus a times 1, a, 4 plus a times 0, 4. Okay. So any point on this line can be decided by giving a and 4 is the y-axis, right? So this is a general expression for any point on this line. Now I go and substitute x1 equal to a and x2 equal to 4 in my function here. So everything will be as a function of a. So once I get that, I get this function. This is a function of alpha or a here. Okay, so a and alpha is same here. Okay, now it's a single variable problem. So this 2 variable is converted into a single variable by using this transformation. And now all I have to do is use the optimality conditions, the first order condition and the second order condition. When I do the first order, take a derivative of this, put equal to 0, I find there is only one minima, and that is 2.083. Now I do the second derivative and I substitute this a star, I find it to be positive. So that means it's a minima. And now I go and substitute this 2.083 here, and I get the new point. I get my optimum point x1. Okay, now this is a line search which is often used in a multi-variable optimization problem. Many times you do this. So here is an example that I start with this, I do a line search along a direction, I get the best point, then I do another line search along another direction, and I get the best point. I keep doing this process, and the whole process will bring me to the minima. Okay, so we'll talk about multivariable a little later. Okay, I think I was told that there should be tea now. Can someone check if we have tea outside for a break? Otherwise, I will continue. Yeah, search directions are given. So search direction is given, and the initial point is also given. So xt and st are given. Only thing unknown is a. So this line search just finds that a.
How do you know it's a global minima?
There is no way to know global minima. As I said, all these point-based methods, they can only find local minima. There is no way to know that these are global minima. Available? Okay, so we'll take a quick break of 5 minutes, and then we'll start from here. Saddle point or inflection point is the same thing. Mathematics people talk about inflection point, and saddle point is talked mostly by engineers. So it's just the from where it's coming from, but the properties are the same. They're talking exactly the same thing. What point you're talking about? Yeah. By the line search, you mean? Line search is not going to give you the optima of the original problem. It just gives you the optima along a line, right? So you're in this two-dimensional case, your optima may be here, but if your line is not going through it, you're not going to find it. You specified the line, and all it can do is go along the line and give you the best point along that line. That becomes a part of a multi-object, multi-variable optimization, which I'll come later. Okay.
In previous class, these variables are neglected. Why these the variables are neglected?
Not neglected, I have substituted, because there is a relation with y1 equal to, somewhere we have written y1 is equal to y11 plus y22, right? So since I know this, I don't have to have all 4 of them as variables. If I have these 3, this one I can derive. That's why I said I don't need to have y1 as a variable. Is that clear or not?
Sir, Z1 this Z1 or Z12 or Z1.
Also, I have written down another set of like these ones. You see, Z11 can be written as a function of y11 and y21. So I don't need to have Z11 as a variable. Okay. So if you have such simple substitutions, you don't call Z11 a variable, Y11 is a variable, because if you call all the 3 as variables, your algorithm is creating numbers at random, right, to start with, and they will not match. If you randomly create Z11, Y11, Y21, do you think there's going to match exactly like this? Left hand side will not be equal to right hand side. So you are making the problem more difficult for the algorithm. Since you know this, you can always say, I don't want to have Z11 as a variable for my algorithm. I want to only keep these 2 as my variables, and I derive the Z11 from it. If I need anywhere Z11, I will compute from Y11 and Y21 the Z1, and then I substitute that Z1 here.
We have to substitute these.
Yeah. But this is not my variable. Algorithm is not changing this. Algorithm is changing this, but whatever value you have here, the algorithm will first compute Z11 using this formula, and then use that anywhere Z11 comes in. So that's where you're always saying I'm always satisfying this, right? That's the idea.
Sir, here variable bounds are not understandable.
In this case, variable bounds are not given, so only the lower bound is known. The upper bound is not known because we don't know what will be the upper bound, except for x1 and x2. The upper bounds are given.
They are given
Capacity.
x1 less than
X1, you have both lower and upper bound. Yeah, yeah.
That is not a constraint.
That we don't consider as a constraint, but the classical algorithms consider that as constraint. But in
they mentioned the constraints.
that's fine. You can either put as a constraint or as a variable bound. Now it depends on the algorithm you're using. If you're using some algorithm that do not automatically consider bounds as bounds, you have to treat them as constraints. But when we get to the population-based methods, bounds are not considered as a constraint. We never go out of the bound. The way we create points always within this. We deliberately maintain it.
0 to 4 we are given.
Right. So you don't have to have that as a constraint anymore because you already satisfied. So it depends on the algorithm. So when you formulate, you can put it either as a constraint or as a variable bounds. Doesn't matter. But then when you choose the algorithm, you have to now appropriately put it.
How can you know that this algorithm is at the local minimum this algorithm?
So we'll talk about all these. You will get to know.
Initially we don't know the optimal form.
Right.
How can you judge this is our answer is correct?
Yeah, hold on to these questions. We'll talk about. Yeah.
This constant thing and variable bounds, it is very difficult to choose whether
Bounds.
Yes.
No. Bounds are
this,
given to your
for
problem.
this type of problem.
Mhm.
But for problem number 1, it is not difficult to
Choose the boundary
Yes.
as for
This problem was difficult, you mean?
Yes.
Because the first time you're doing it. First time you're doing it, so there are a lot of dependencies. Understanding the problem requires some time. That's why I said 50 to 60% efforts goes in understanding the problem. So it's not like you get a problem from somewhere and you know everything about it. You have to go and visit the guy, talk about. A lot of time goes in understanding what the problem is. Otherwise, you are solving a different problem. And it's an iterative process. First time you never get it. I never got it right the first time. So we have to do at least few trips to finally understand what they're saying, because the person you're talking to are not optimization person as well. So he doesn't know what you are looking for. To him, everything is a magic you are doing. Okay. So he tell you half the thing. He doesn't tell you half the thing. If only you ask him, he will tell you another thing. So, but he's interested in solving the problem. He just doesn't know how much to tell you. So, okay, you got something, whatever you got. Instead of going too far, he can get annoyed that you're asking too many questions. So you say, okay, I understood something. You go and do some job, get a result, go to him. Then he tells you some more thing. Now you hooked him up. You're showing him some results. He's seeing some good things, but some not so good things. So he'll say, no, this part I'm not happy. Then you try to find out why you're not happy. He will say, oh, this condition is not satisfied. Then you realize he's telling you this for the first time. So you say, okay, now I understand. So I'll put that as a constraint and again go back to him. So that's always, so you're solving it for the first time. But we discussed this. So for the homework purposes, you have done whatever you could. But I know that this is not from your domain. So, I mean, some of you may not get it. So it's okay.
Sir, if we have some more examples, then
Yeah,
it's
exactly.
easier to us.
Exactly. So
Some more
So this course, we are not doing a formulation course. Okay, we are talking about the optimization algorithms and how they work, the properties of optimal solutions. So I just wanted to spend one day on the formulation aspect, but every formulation is different. If in your area, your problem, it will be some kind of formulation. When you move to another person's, it will be different. So I cannot do it for every problem. Okay, so the best thing is, you have understood now that there are certain constraints and objective functions, variable identification, variable bound identification. All these you need to do in a formulation, and it involves domain knowledge, right? That much is enough. Then when you get a actual problem to solve in your thesis, like if you're doing a robotics problem, you need to now formulate what is the objective function. Then everything will come back to you, okay? And then you will doing. So I think the way to get the formulation a little more is read some papers on optimization in your area and see what they have done, what kind of objective functions they have written and constraint sources they have. That much and my book has few more example problems. In the slides, I have given you one or two more example problems, so you can maybe go through some of those, whichever falls in your area, if it falls. Otherwise, you need to look into the literature. Okay.
Thank you.
Yeah.
For the next point, how we have to go for the direction?
I will tell you that. I have not told the whole algorithm yet. Yeah, we will talk about it. Okay, can we call others, please? Okay, let's continue. I'm not sure if they're recording. Okay, let us begin. Maybe they'll catch up. So now let's talk about algorithms for single variable. So this is theory that we just talked about, right? When you have a function as a function of one variable, there is an optima, and what properties the optimal solution will satisfy. So there's a first order condition, there's a second order condition. If second order condition doesn't satisfy, you have to go to third, fourth, and all that. We've looked at that, right? And we also quickly saw how that can be used as a line search in a multi-dimensional space, but we will get back to multivariable optimization later. We're still with single variable. Now we're talking about numerical algorithms. Okay, it's not using the theory that derivative equal to 0 and second derivative positive. We're talking about now a numerical method. Now in single variable optimization, there are two steps of finding the minima. First step is called the rough bounding step, where our goal is to not find the minima exactly, but we are going to bracket the minima. So it's still a single variable, right? So we have an x-axis with the x, and y-axis is the function. Okay, somewhere there's a minima. So it can look like this, for example. So there is a minima. There is a function here, and there is a minima somewhere. I have a one variable x. So I need to locate where the minima is. So the job of the first step here, the rough bounding phase, is to find a lower bound and an upper bound within which the optima is guaranteed to lie. Now, if you can make that bound as tight as possible, that will be the goal here. But the whole idea is to have a minimum, a lower bound and upper bound within which the optima lies. Then the second step is now restricted within this lower and upper bound that you found in the step 1, and do a much better job of finding the optima with precision, arbitrary precision. The second job, we are going to nail the optima, but first step is to just get a lower and upper bound. Is that all right? So these are two steps that are followed for single variable optimization. It is a big assumption in all of these algorithms, point-based methods, is there exists only one optima in the entire search space. So there is no local or global. It assumes there is one optima. Where is the optima? We don't know. But that doesn't mean these algorithms don't work when you have multiple optima. You may have to do some trial and error. Some one time you may not get it. You may have to do few more time. But that's how the whole classical literature is. Now here you're talking about any function, nonlinear, differentiable, non-differentiable, anything. Okay, so that's the flexibility we have here. So I'm going to show you one method for the step 1. That's called the bounding phase method, but there are a few other methods. Okay, what you do here, you need two things to start. First, one point, which is x0. That's your initial point. You give that as any point. It could be 0, x equal to 0, it could be anything. Okay, and you also have to supply a step length, a step, call it a delta. Okay. Now, very beginning, what you do is figure out whether you should go in the positive delta direction or in the negative delta direction from x0 in order to bracket the minima. First, you need to do that. In one variable, there's only two directions, plus or minus, right? Okay, so how do you do that? What you do is you compute three things. So you go x0, a delta amount in the positive direction, and you can go delta in the negative direction. So you have these different situations. One situation can be this, that as you are going from x0 to positive delta and negative delta, there is a monotonic reduction. So something like this happens. That as you are going in the positive x direction from x0, so this will be then called x0 minus delta, x0 and x0 plus delta. You have a reduction in value. Then you say delta is positive, because if you go in the positive direction, you can get the minima. What if this happens, that x0 minus delta is smaller than x0, then x0 plus delta? These are the function values. Then you change the sign of delta. That means you have to go in the negative direction, right? Because looks like if you assume there's only one minima, this is the direction. If you go, you'll find the minima. So you have to change the sign of delta. What if this situation happened? x0 is in the middle, plus minus delta and this has a highest value, and these two are smaller than that. Then what happens? Which direction do you go?
Go to the smaller side. The direction which is the smaller side. Go to the negative side.
Well, if you assume only one minima, you don't know which way it is. I mean, the fact that this one locally is better doesn't mean the minima. So there may be a minima here, there may be a minima here, and you don't know which way to go. So we just blame it on these points that you have chosen. Say you have not chosen the right kind of point. So you change the x0 to some other x0 and repeat the process till you don't have this situation. That's the simplest way to avoid this. How about this when you have?
You're already at the minimum.
You are already?
At the minimum.
No, you've already bracketed the minima. This may not be the minima, because there could be a function that dips quite a bit and moving up. So you don't know that any of them, but you at least know that you have bracketed the minima. So you don't have to use this algorithm anymore. You're so lucky that you have chosen a x0 and a delta that brackets the minima, and the whole goal here was to bracket the minima, and you have done it at the very first step. So you don't have to proceed with the algorithm. Your bounds is x0 minus delta and x0 plus delta. But that will probably not happen, because you cannot be so lucky every time, right? So usually it will be one of these two situations, that you found a x0 and the direction to go, plus or minus delta. So then your sign takes care of this. Now you start the algorithm. So first you do is look at x0 and x1. So x1 is delta times away from x0, and this formula will give you that when k is equal to 2, then 2 to the 0 is 1. So you have x1 plus delta will be, so this is giving you x2, but before that you have x0 and x1, because x1 is already evaluated when you did this delta determination, right, plus minus. So, and let's say you found x1 better than x0, and that's why you are moving in that direction, right? So your first step is already done when you've decided delta. Now your k is equal to 2. Now you're going to the x2 point. So x2 point is x1 plus 1 times delta. So delta. So you actually go delta times away from x1. Now what you do is compare x2 with x1, their function values. So x2 with x1 I compare. If x2 is better than x1, the new point has a smaller value. I'm minimizing by default, okay? So if this is smaller than that, I continue because there is a scope of getting even better. So I continue. That means what I do, I increase k equal to 3. And I come here. So now x3 is going to be what now? x2 plus 2 times delta. So now I move 2 delta from x2. Okay, and I compare again x3 with x2, and I still find x3 is better. So now I make k equal to 4. So my x4 is going to be x3 plus 4 times delta. So I go 4 times delta. Again I see better. Now I go 8 times delta. So every iteration you are moving double to what you have done. So you exponentially approach the minima. What happens here? Here I still see x5 is smaller than x4. Although this picture is there that tells me I have crossed the optimum already, but the algorithm doesn't know that. It's going with this algorithm that as long as the new one is smaller than the previous one, you still continue. So the algorithm will say continue and go k equal to 6. So k equal to 6, I will go 16 delta. Now I come here and this one I compare with that one and I say, oh, now I'm worse. So algorithm says stop, don't go further because you've already crossed the minima. Now what are the two bracketing? Not x5 in x6, right? Huh? Not x0 and x6. I could do better. x4 and x6. x4 and x6, right? So that will be the best thing that I could do. So you actually go xk minus 2 to xk, where you've stopped. So in this case, I stopped at x6. So I will do x4, comma x6. So this is the lower bound, that's the upper bound. Simply because I don't know the cross, when this one is smaller than this, whether the optima was inside or optima would be here. I have no idea. So just to not have that situation, we go x4 and x6. Is that clear? So if your x0 is far away from where the optima is, you are exponentially approaching, right? 1 delta, 2 delta, 3 delta, 4 delta, 8 delta, like that. So eventually you may have a lot of delta. So your bound can be quite big, but we don't care because all we try to do is bracket the minima. So, but if you start very close to the minima, then you will not go that far to cross it. So your bound is going to be tight. But it doesn't matter. Even if you're far away, you're going to very quickly get there. Now, one of the parameters, so what is the parameter of this algorithm? I said every algorithm has a parameter. Huh? Step length delta, of course, is one parameter. Is there? x0, usually not a parameter, it's called the initial point. Okay, so that of course depends on the algorithm, that initial point. But delta is a parameter for sure. Number 2 here is a parameter. Because twice you are moving you can make it 1.5. So your bound is going to be a little tight. So every time you're going 1.5, then 1.5 square, then 1.5 cube, and so on and so forth, your bound is going to be tight, but it may take a long time to reach there because you are not moving very fast now. So in optimization algorithm, that's always the trade-off. How fast you want to move to the optima versus with what accuracy you arrive there. This is always a trade-off. And in an algorithm, sometimes you need to do this trial and error to figure out is 2 is the right number for my problem or 1.1 is the right number for my problem. So you need to do some of this. But whoever has developed that method suggested to use 2. Okay?
So in this case, if certainly we get trapped in an asymptotic curve, then
what do you mean? Like, we are assuming there is a single minima. Yeah.
Suppose the curve has one minima and then an asymptotic part.
Then there are more than one minima. Then this algorithm is not valid. You can use it with the proper choice of x0 and delta, but the algorithm is not guaranteed. But this algorithm is guaranteed to bracket if you have single minima.